So let's go back and look at our optical spectroscopy setup. So now we have discussed several different light sources over here, which create broadband radiation. And then our broadband radiation will pass through our sample, but then, as we discussed in the beginning, we have to divide the different wavelengths up in different directions like we see up here. So next we're going to talk about the spectral resolution instruments. But while we talk at them, we will also go back and discuss some light sources which is also useful for spectroscopy, but we'll talk about that during at the same time as we discuss spectral resolution instruments. So the first spectrally resolving instrument we're going to talk about is a Prism spectrometer, just like we saw in the picture above. So here we are using the index of refraction of a material. So in this case we have down here we have a wavelength, and here we have an index of refraction of different material, and we're going to come back to index of refraction, why we have index of refraction and why it changes with wavelength. But what we can see here is as we go to lower wavelengths, the index of refraction becomes bigger. This is normally called dispersion. So you're all familiar with that if we have light impinging on a piece of glass with index of refraction, the direction of this light beam will be changed as you go in. And the size of this change is given by Snell's law of refraction, which is basically what we have over here. The index of refraction for the first material times the sine alpha of the incident beam here is equal to the index of refraction of the material afterwards times sine of this angle coming out. So this is how the beam changes angle. Now we would like to use this to measure what wavelength the light has which comes into our spectrometer. So here we have a spectrometer, a setup of a spectrometer. And so we start off with having the light which we want to analyze, we focus it on a small slit. So that's basically so that we should get that all the light is coming from a fairly small point. And then the light goes out from this slit and it expands out like we see here. And if we put a lens exactly one focal length away from this slit, then after the lens we will have a collimated beam. So that means that the light coming out after this lens is parallel. And we let this come into and hit the prism. And when we hit the first facet of a prism, the direction of a beam is changed. And then we hit the second facet of a prism, and then the direction of a beam is changed again. So, and how much change we have depends on which wavelength of the light we have, because we have different index of refraction for these two wavelengths. So that means for one wavelength we have a beam coming out like the top beam here, and for the other wavelength we have a beam coming out like the lower beam here with different directions. And now in principle we could just take and put something very, very far away, and if we just let this beam travel for a very long distance, we will be able to see that they have different directions. But we would like to make a compact spectrometer. So to do that we put in a lens. So we put in a lens here and we basically image infinity away on the focal plane of this lens. So that means that depending on what direction the beam has into the lens, it will be focused to different spots. And over here we then have a detector which can detect the light in all these different spots, like we looked at before, for example, a CCD or a CMOS detector. And we will talk more about them. Okay, so how good is such a spectrometer? Well, that's given by something called resolving power, and it's denoted by R. And that is the wavelength of light coming in divided by the smallest change of wavelength we can see. So let's just take an example of this. Let's say we are at 1,000 nanometers and we can see a difference. So if a light changes wavelength 1 nanometer, we can see it. Then our resolving power is 1,000. And this resolving power is given by G, which is the length of this prism, I'll come back to that, times the derivative of index of refraction with respect to wavelength. So that is basically the tilt of this curve here. So it's the direction of coefficient for this curve over here. So this definition actually holds if you fill the whole of a side of this prism here. So if you fill the whole of a prism, this gives you your resolving problem. And it's limited by how small the smaller this slit is, but of course then you get less light through, and also the size of your prism, how large your prism is. Just as an interesting fact, Snell's laws was written down by Snell in the early 17th century, but actually it was discovered much earlier than that. It was discovered by a guy named Ibn Saul in Baghdad in 1984, when he wrote down the same law, which later became known as Snell's law. So we just stated that we had an index of refraction, and as I promised, we're going to now go over and have a look, do a bit of a deep dive into what is actually index of refraction. What is the microscopic cause of index of refraction? And we'll do this because it also touches on things like what is absorption, which is of course highly relevant for this course. But it will be a little bit of a detour, so let's start with looking at radiating atoms and moving charges. So in the first picture here, we have an electron which is sitting around a nuclei, and the electron is negatively charged. And now we are going to, as we move on, we're actually going to look on what happens when we have quickly varying fields, even though in the second picture here we haven't applied a static E field. But since it's going to be quickly moving fields, it's mainly the electron cloud. So this, what we see here, it's the wave function of the electron, what is the probability distribution to where to find the electron, the wave function of electron. Or rather, the probability distribution is the square of this. But anyway, okay, so we apply an electric field, and since the nuclei are heavy, if we have a varying electric field, that's basically not going to move very much because it weighs a lot more than the electron. But the electron cloud is going to be displaced. Now we want to construct a hand-waving description of a hand-waving quantum mechanical description of this displacement of electron. And to do that, we add an excited state. So this is the wave function of an excited state. And the blue here and the red here corresponds to the sign of the wave function. So it has nothing to do with the charge of electron or anything like this. This is simply blue corresponds to a positive sign of a wave function, and red corresponds to a negative sign of a wave function. So if we now add the ground state together with the excited state, what do we get? Well, since it's positive here and positive here, this becomes stronger. So this is E plus G. We are adding the two wave functions together. But since the sign of the wave function is negative here and positive up here, we will actually get a lower probability up here. So this means that our wave function will be skewed towards the bottom here, and this is the hand-waving quantum mechanical description of this displacement that the electron is down here. So what we have described now is the displacement of the electron cloud as a superposition between a mixed state between the ground state and the excited state. Now there's an energy difference between the ground state and the excited state, and the sign of the excited state will evolve, or the difference between these two will evolve with a difference energy. So if we wait for a while, what's going to happen is that the sign of this is going to change, and when we add them together, we're going to have a term here in front of it which change, and this will turn into minus sign, and when we add them together, they instead are constructively interferes up here instead. So that means at some one time point we have an electron looking down here, and if we wait for a little while, if we have it in a superposition, the electron is up here. And the energy difference between these two states, so I've written it here, this is the energy difference, is given by Planck's constant times the frequency of this oscillation between being in one state and being in the other. So that's the difference frequency between these two. So The first case we're going to be looking at is if we come in with a field which is varying up and down, which is exactly matching the transition frequency between the ground state and the excited state. And this gives rise, as you might guess, to absorption. Okay, so we have some light incoming over here. It's exactly resonant with this transition. And here I have drawn the incoming light as a function of time. So this is just simply the varying E field of incoming light. And here we have some electron surrounding some atoms. So when this incoming light hits these electrons, it will put them into a superposition, and we are smack on resonance with a transition frequency. So if we draw that we are absolutely resonant here, as we normally draw it when we are looking at spectroscopy, like an absorbing line like this, we are centered on this line. Okay, so we are on resonance. When we are on resonance, these electrons will the probability of where to find the electron will start oscillating, like we saw in the previous picture. So when we have electrons oscillating, like we talked about when we talked about synchronous radiation, accelerating charges, they will emit radiation. So these accelerating charges will emit radiation. So these moving charges, they will be emitting radiation. So I'll draw that here with a red arrow. And I will get back to this in the next slide. But the radiation, the movement of these electrons are 90 degrees after in phase with incoming light. 90 degrees after. But there is also a geometrical contribution, which is another 90 degrees. So in total, the emitted light is 180 degrees out of phase with incoming light. So let me draw that out. So the green here was the incoming light, and the light emitted by these electrons which are moving is this other curve here. So we have, and the light which is emitted is 180 degrees out with phase. So when we now add these two together, these two interfere. That means we take this one and we add it with this one, we get the brown light, and over here we can draw the brown light like this. So that means we have less light. So after our light has passed these atoms, we have less light left. That's what we normally call absorption. So this is very important. Absorption it's not like magically the light disappears, but rather the absorption is an interference process between the incoming light and the light emitted by these electrons. And again, there was two contributions to the phase shift. 90 degrees phase after, as we see in the next slide, these are oscillating 90 degrees after in phase, and then there's another 90 degrees, which is a geometrical factor. And when we have a questioning hour later on, I'm very happy to discuss this geometrical factor. So please come and ask me if you're interested. But right now, we'll just say that there is a geometrical factor. Okay, so we looked at our absorption line here, which was the same thing as the transition over here, and we were smack on the middle of this. Okay, so I will make a new graph, which I stole from somewhere. The red curve here is again the same red curve we had in the previous graph, and we are on resonance here. And this here is a graph for a harmonic oscillator. And the electrons, the forces holding the electrons classically to your nucleus could sort of be thought of as a harmonic oscillator with forces restoring the electrons to their symmetrical state. Okay, anyway, so if you look now when we are on resonance, this blue curve here shows the phase of your oscillator compared to the driving force. So if we are on resonance here, we are smack in the middle, you go over here and you look at the phase, you see I have 0 here, minus 180 here, and here on resonance you are minus 90 degrees in phase. That's what I said with electrons in the last slide. On resonance, the electrons' movement are 90 degrees after the driving field. But if we look far below resonance down here, you see it's 0 degrees. And this is where we have index of refraction. So we're soon going to come back to that, but I want to make another little detour before we get there. So between when we are on resonance and when we're far below resonance, there is a 90-degree difference in phase. Okay, now let's give an example of a harmonic oscillator on resonance. So here we have a harmonic oscillator. We have this curve here, it's the red, and we're on resonance. And this here is the phase, and now the phase is flipped the other side because we have a different convention than in the previous picture. But anyway, we're shifting 90 degrees in phase here on resonance. So what we have here is we have a driving force. We're pulling this spring up and down, and we have a weight, and this weight and spring system, like you know, has a resonance frequency. And if we now go on resonance, that means that this thing will, the weight will oscillate faster and faster and faster with higher and higher amplitude. So we will get a very high amplitude for our emission. Okay, so let's now move and go far below, so we're much lower frequency. So now we're moving this really slowly, as you see this graph up here. So we are far below resonance here. Okay, so now you again see this oscillation, the same oscillation as down here, and that's just because when we start abruptly here, we also put a little bit of energy up to here, so we'll have some oscillation, but so you can see that oscillation dies out and is much smaller as only after this part of the simulation. That's not the one we're interested in. The one we're interested in is this slow oscillation where it goes down here and then it goes up here, and you see this oscillation follows the driving force up here. So if we're below resonance, we have a much smaller, with two things. We are in phase with a driving force, and the other thing is the amplitude of these oscillations is much smaller. So the further away we are, the further away we are from the resonance, the smaller the amplitude response is of our harmonic oscillator. Okay, so now we're going to move on to the index of refraction part. And let me just first show you here, but what we're going to be looking at now, I have swapped this around, so now I have frequency, not wavelength down here. And you see as we go to higher frequencies, we have a higher index of refraction. So I'm going to tell you why we have an index of refraction overall, and then I'm going to tell you how this increase in index of refraction is connected to absorption deep down in the UV, or in this graph where we have frequency at high frequencies. Okay, so now we are coming in with a driving field which is far below the resonance frequencies of the material. So let me go back. So in our optical material, we have some resonance, but we come in with light here, which is far away from these resonances. So what will happen now? As we come in with light, we will again put a little bit of excitations into the electron cloud. And the electron cloud will give a little bit of oscillations. But there's two differences from last time. Since we are far away from resonance frequency, the amount of energy we transfer will be very small. So that's one thing. So this oscillation will be very small. The second thing is that we will have a 90-degree phase shift will not be there. We will be moving these electrons in phase with a driving field. But we'll still, you remember from last time, we had a 90-degree phase shift of emitted light coming out from these, which came from geometry. So that phase shift we still have. So the total phase shift for the light coming out, so this is the light coming out being emitted by all these moving electrons, is now 90 degrees compared to the incoming field. What does this mean? Well, if we study this a little bit more carefully, we see here where we have a maximum the maximum of the electric field of incoming light, the field emitted by the moving electrons is 0, so it won't become any higher here. And the same over here, where this is the maximum negative, it's 0, so it won't become any lower. So the amplitude of the electric field, if we add these two together, so we add this field and this field together, to first order, the amplitude won't change. But over here, this part here, where we are going up, this thing is always positive. So that means if we add these two together, we have to draw a curve which is above this curve here. But then it's not higher. And for the whole part here we are going down, this curve is negative. So that means here we have to draw a curve which is slightly lower, and then here again we have to draw a curve which is slightly higher, and so on. So if I draw in this curve, it looks like this. So what does this look like? Well, it looks like a phase shift. So that means our intensity has not changed like it did when we had absorption, but we get a phase shift. So this is the total light. If we add the incoming light with the light emitted from the atoms, we get a phase shift of a light. And we get this for every layer of the material, we get a phase shift. So I mean, as we continuously move through the material, we have more and more phase shift. So that gives rise to two things. Firstly, we have our phase shift in each layer, and since we have it all the way through, that gives us a shorter wavelength in total as we look in the material. And this is what we call index of refraction. So again, index of refraction is an interference effect between the incoming light and the light emitted by the oscillating charges inside your glass, predominantly the light charges, electrons. Okay, so let's now draw the picture from the last slide again, where we said that, okay, this comes from these absorptions which are far down in the UV or at very high frequencies. So as we move closer and closer to these absorptions, that means that the oscillations will be bigger and bigger. So that means that this brown emission, the red emission here will be bigger and bigger, and that means that the phase shift will be bigger and bigger. And that gives rise to the dispersion. So this dispersion here is caused by getting closer and closer to the resonance frequencies, and thereby having a larger red emission. So let's write that down. So here are the absorption. So if we are close to the absorption, we have large emission and we have large change of index of refraction. So you have a large index of refraction. Large change which leads to a large index of refraction. So with this little detour, we have explained both what is absorption and what is index of refraction. And so now we know why are these curves bent up, and why do we have a larger change of angle as we go through this spectrometer, which is based on index of refraction changes. So the last thing I would like to add is just a few of the limitations here. So one, this resolving power requires a very small slit, so that's not included in the resolving power. And secondly, as you see, the resolving power is dependent on the derivative of the index of refraction with respect to the wavelength, and you can very clearly see here in this graph as this is not constant. So if you want to use it over a slightly larger wavelength range, you have to take this into account. But this can of course in principle be done in software. So let's go to the next spectrally resolve, the next instrument which can do spectrally resolution, and this is a grating spectrometer. So I will start talking about the grating and how the different wavelengths are separated with a grating, and then I will go on and show a grating spectrometer and go through the different parts of this grating spectrometer. And up here you see a very large grating, so these can be very large, and here you have light coming from somewhere, and depending on the different positions you look at the grating, there are different angles, and therefore you see the different colors. It's a very pretty picture. To discuss how a grating spectrometer works, I will start off describing how the grating works, and I will use a very simple setup or geometry which I show over here, which is the so-called lithro geometry, where the beam of light coming in and hitting the grating is diffracted back in exactly the same direction as it came from. And if we now look in the direction of this beam coming in here, what we have is that in the direction of a beam, the distance between one groove and the next groove is exactly half a wavelength. So what does that mean? Well, if we compare, for example, this tooth in the grating and the next tooth in the grating in the direction of this beam, the light diffracted from one tooth, which is diffracted in a very large angle because this tooth is so little that it diffracts in a very large angle going out from a single from a single groove. And the same goes for the next groove, which is also small and diffracts in all angle. But the light diffracted from this one, from the next one compared to the light diffracted from one before, has traveled half a wavelength down and then another half a wavelength back. So it has traveled exactly one wavelength longer in this direction here. And so that it's going back exactly the opposite direction to the incoming beam. And since they differ with exactly one wavelength, that means that these two are interfering constructively in this direction because they have exactly the same phase in this direction. And if you were to take some other direction, this would no longer be true. So, okay, so we have one beam. We have one beam, incoming beam, so that we'll draw that here. And then we have one diffracted beam going exactly back, in the exact tracking back. So that means these two beams are interfering together, and we have two counter-propagating beams interfering. If we look at them together, we will get a standing wave. So what we have here is a standing wave pattern with a node. There is one node on each groove, and the nodes here are in a standing wave pattern. They are separated by half a wavelength. If we now take the slightly more general case, that means that we have a beam coming in from this direction with an angle alpha compared to the grating normal, and then it's diffracted away in an angle beta compared to the grating normal. Then the light coming in here has traveled the same way. These two beams which we are drawing here, which is a plane wavefront, it has traveled the same distance up until this point here and over here. So that's drawn in blue. And if we now look at the light which leaves it, after this point here along this line and to a target infinitely far away, they have the same distance. So the difference in distance traveled is that this line which we draw here travels this much further, and this line over here travels from here to here further. So if we want to look at the difference in these two travels, we take this distance here from here to here, which is given of d times sine alpha, where d is the distance between two grooves, minus this distance which is in black here, which is d sine beta. And if we subtract these two, we get the difference they have traveled, just like we did in the previous one. So delta S for these two lines is equal to d sine alpha minus sine beta. And if this is equal to one wavelength, then we will get constructive interference. So that's what we write over here. So if this distance here is equal to lambda, we'll get constructive interference. But that's not the only time we get constructive interference. We can also get constructive interference if this distance is equal to 2 lambda or 3 lambda or 4 lambda. So in the general, we have to have a integer number in front of this. Anytime we have an integer number here in front of it, m being an integer number, this holds true and we get constructive interference. And m here is called diffraction order. And m can be both positive and negative because either of these can be bigger. So now we know when we get constructive interference. Let's now try and look at how we use this in a spectrometer. Oh yeah, but first we should look at the resolving power, the ultimate resolving power for a grating spectrometer. And again, the resolving power is the wavelength over how small wavelength change you can see. And this is called R. And in this case, N here is number of illuminated lines. So that means that's how many grooves we illuminate. So in this case here, we illuminate 1, 2, 3, 4, 5, 6 grooves. So in this case, this would be 6, and M is the order from over here. This gives us the resolving power. Okay, so let's go through the light through this, and this is actually a monochromator, not a spectrometer. But I will tell you what the differences are. They look very much the same. Okay, so we have some light source here, and then we have some light which focus the lens onto a small slit. So that's a small opening, so that all the light comes from one point. And that's just the same thing as we had when we looked at the prism spectrometer. So the light expands out, and now in the same way we want to create a beam which is collimated, so all the light is parallel. And we do that by having a mirror in this case instead of a lens. So we are focusing the beam with a mirror over here. So that means that after this mirror we have light which is parallel, and here we have alpha, which is the input angle, and beta, which is the angle coming out, just the same as in this drawing down here. And then in this case the light comes out and collimated, and different colors comes out and being collimated in different directions. And then we have a focusing mirror, which again we could have put the detector infinitely far away, but that's of course very impractical. So we image the infinite onto a slit over here, and in this case it's a slit because it's a monochromator, so this will select a single wavelength. But if we instead put a detector here, a spatial detector over in this position, different colors will come out in different directions, and that means that if we have a spatial detector here, we can detect which color is coming out. Now in a monochromator you could move a slit over here depending on what color you wanted to detect. But normally instead what you do is you turn the grating, because that's easier, and then you keep the detector in one position all the time. So by turning the grating you select alpha and beta and which wavelength should come to the detector over here. So with a monochromator you select one wavelength, and then with a spectrometer you have a position sensitive detector which can detect many wavelengths at the same time. Okay, let's next look at a real life example of a spectrometer. And so this thing, the spectrometer here happens to be an Ocean Optics USB 4000. And if we start down here you can attach a fiber so that you can lead the light to the detector by a fiber. And from this the light is expanded out, and over here it hits a collimating mirror. So here you have a collimated beam of light, and it creates a collimated beam which hits the grating, which sits underneath here. And from the grating different colors comes out in different directions. So from here different color goes out in different directions. And over here we have a focusing mirror. So after here we are focusing down to the detector which sits over here, so that different colors are focused to different spots. So over here the blue light is focused, and over here the more reddish light. And these kind of spectrometers can be found for many different wavelengths. Okay, so I just want to keep this picture so that we have this picture with us. Okay, so now I'm here as well. So let me now show you. Here I have a spectrometer just like the one above, and you see if you look down here there is a fiber going into it. But let me turn it around so that you have it in the same way as you do in the picture. So that's from the back here. So let me start down here. So here we have an end where I can remove this yellow cap, and then the light can go in through the end down here. And then the light goes through, let me see so you see it, through the fiber like this, and then it comes up to here. So it goes in through here. So this is where the light enters. And then it goes through just like in the picture you see above. And then at the other end over here, it sits the detector, and then the signal from the detector is read out via USB over here. So now I will use this to analyze light from a few different sources as an example. Let me put this down. Okay. So above me I have a fluorescent tube. I will just fold it back like this so that you can see it. You see there's a fluorescent tube. It's just a classical fluorescent tube. And I will also analyze the light from one of these. I will turn it on here so you can see it. It's one of these normal headlights, and inside it is a white LED. We'll talk a little bit about how they work. And I will also analyze the light from a red LED, which I have behind me here, which it just sits on a power supply, so you will see what that looks like as well. Okay, so I will swap so that you can see the output from the spectrometer. Okay, so here we have the window from the spectrometer. So down here it's not so easy, but here it says 400, 450, 500, and so I'm up to 800 nanometers up here. And it's also color coded. I mean, this is false color coded by the program. And the higher the light we have, the higher it will go here. So let me start off by looking at a red LED. So let me see if I can find it here. So here we go. So there is there we have an LED, red LED. I can pause it here. Okay, so we can now see that this is a single color red LED, and we can see that the peak emission here is about, for this particular LED, is about 630 nanometers. So a single color LED like this, you see it's fairly smooth. So this could be, if you only want to do spectroscopy within a limited range, this kind of LED could be an interesting light source for an application. And you can buy narrow LEDs like this in many different colors all over the spectrum to suit the application you have in mind. Okay, so next I will point it out through the window. So now I'm pointing it at the sky and I'm trying to get a reasonable reading here. So I'll just pause it here so that you can. So this is the spectrum for the sky. And if you would like to, you can probably look up and see where the different absorptions here. I think that this one over here, if I remember correctly, comes from ozone, for example. And there are also at longer wavelengths there's absorption features from the water in the atmosphere. So next I will look at this light here, which has a white LED. So let me put it down here so I can get the light from it and put a pause on this. Okay, so why does this light source look like this? So if we see, it has one peak here and then it has a large peak here. So let me quickly change slide here. So this slide here is from Wikipedia. And you see it looks very similar, but on the Wikipedia page, this one here is much larger and this one here is much smaller, but you can still see that it has the same shape roughly. And so the first one here, this peak here, this is a gallium nitride or Indian gallium nitride LED. So this is a blue LED. And then this light over here, this comes from a cerium doped YAG crystal. This can of course also be a very interesting light source for spectroscopy application. You see it's fairly smooth, it covers a large part of the visible range. There's a little bit here where there's no light. So you have to be a little bit careful, but you can of course select different white LEDs and they have slightly different spec. Okay, so now first we will start to discuss this peak here. So the first peak. So here we have a picture of LED, and the LED has one p-doped region and one n-doped region, and where you put a voltage across this PN junction. What we get now is that we have in the conduction band here we have electrons and they move into the middle, and down here in the valence band we have holes where there are missing electrons, and they also move into this combination region. And when the electron falls into the lower energy levels, which is the holes down here, and combine with the holes, they release energy in form of a photon, and then we get this photon coming out. So that's the short version of how a light emitting diode works. So that was that part. Let's go to the next part. So the light in this part does not come directly from the light emitting diode. It actually comes from cerium doped YAG, and YAG is Y3AL5O12. So that's a crystal, and this is a powder which lies on the outside of the gallium nitride or indium gallium nitride LED. So let's look a little bit on the process which happens inside this powder. So what happens here is we have an energy level diagram, something like the one looking like the one I see here. And the photons coming out from the blue LED, they are absorbed and they excite up to some higher lying level here. And then we have a very fast non-radiative decay down to the level here. And from this level we have fluorescence. So we have coming out from this level we have fluorescence. And this fluorescence can fall down into a broad band down here. So that means we will get fluorescence over a broad wavelength range. And that's what we see. That's the rest of the light we see coming out. And you have heard about this before. So you have absorption here, and then you have a Stokes shift, and then you have a emission. And you have heard about this in previous lectures. So that means that we have the blue LED. This is not exactly, this is just showing the process. This is not the spectrum we had before, but we have a blue LED, and then we have this broad emission which gives the rest of a white light. So that's how most of the white light LEDs works. So here we have a table of overall luminous efficacy for different light sources. So that's how many lumens, which is the amount of light you get per the amount of power you put in the form of watt. So if we saw, for example, look at a halogen bulb, they're about 20 lumens per watt. And if we look at a fluorescent tube, which we will look at the spectrum of one of these a little bit later, they're between 70 and 100 lumens per watt. And if we look at light LEDs, white LEDs like the one we looked at just now, they can be up to 150. They can be up to 150 lumens per watt. And a few years ago, they showed in experimental lights that they can actually be even higher. So they showed up to about 300, or rather, they showed up to about 300 lumens per watt. And commercially, I think they're about 200 lumens per watt. So if all fluorescent tubes are exchanged in lighting application, if all fluorescent tubes are exchanged for efficient LEDs, we can potentially save half of the power. And if you change all the old kind of light bulbs, the gain is much bigger than so. And as you probably have seen, the white light very quickly becomes more powerful and cheaper. So this is governed by something, well, it's not governed by, but it's been described by something called Hight's law, which is the law for, which corresponds to Moore's law for the power of a processor. And it basically states that the cost per lumen falls by a factor of 10 every decade, and the power from each package grows with a factor of 20 for each decade. So these LEDs are very quickly becoming more powerful and cheaper, which of course also makes them very interesting for applications, for example in spectroscopy. And finally, as another example, let us look at the spectrum from a fluorescent tube. So this was the tube above me, which I showed you earlier. So here we have some examples of fluorescent tubes. Let me now just direct the fiber towards the fluorescent tube above me, and I can pause it like this. So again, here we have a spectrum from a fluorescent tube from Wikipedia, and up here we have a spectrum which I just have measured, and I tried to match up the scales in nanometers here. So you can see that there is a rather large agreement between these different. You can also see that the white light coming out from this is not smooth at all. I mean, the white light coming out from a fluorescent tube is a lot of peaks, and we can actually identify what these different peaks are. So let's just firstly describe slightly how a fluorescent light bulb works. So inside the fluorescent tube there is mercury vapor, and what you have a discharge through this mercury vapor. So you pull current from one end, electrical current from one end of a fluorescent tube to the other end of a fluorescent tube. And these electrons bumps into the mercury atoms, and they ionize the gas. And that excites, when we bump into them, that excites the mercury vapor, and this emits light in the ultraviolet range mainly. But peak 2 here, and this peak 1 as well, but it's not really visible here, peak 2 and peak 5 comes directly from the mercury. But all the other peaks do not come directly from mercury, because the inside of a light bulb, this fluorescent tube, is coated with different crystals, just like the cerium YAG crystal we saw earlier for the white LED. But in this case, it's different, like terbium, cerium, and lanthanum and europium doped into different crystals like yttrium oxide and lanthanum phosphide crystals. So I have pulled up a table from Wikipedia where you can actually go down and you can identify where they have identified from what different materials all of these different peaks, which together creates the appearance of white light. And it's fairly obvious that this is not such an easy source to use for spectroscopy, since it has so many peaks. So what I mean with use for spectroscopy is used for light source for an optical spectroscopy setup. What it could be used for is that the peak number 2 here and the peak number 5 here, we sometimes use in the lab to make a rough calibration of our spectrometers, because we know what wavelengths they will be emitted at. And of course, the light from all of these other transitions here, they, in the very same way as when we looked at the cerium in the white light, they come from all the power being emitted in the ultraviolet by the inside the mercury vapor. It hits this layer of these crystal layer on the inside of a tube, excites them, and then they fluoresces, and that's the light comes out, which comes out from the fluorescent tube.